Imagine you're an AI engineer working with a marketing manager who is in charge of weekly ad budgets. Every week, they decide how much to spend on ads and then track the revenue that comes back. Now, they've handed you a dataset covering 10 years of weekly ad spend and revenue. Your task is to analyze this data and build a model that can help guide the future budget decisions. Welcome to AI Lab 99. This is the fifth project in the series. If you're joining in for the first time, feel free to check out the earlier videos to catch up on the foundations. But for now, let's dive straight into the dataset and see what insights we can uncover. All right, let's get started by creating a new Jupyter notebook. We'll begin by importing pandas, one of the most common Python libraries for working with structured data. Then we'll load our digital marketing dataset using readCSV function. Let's take a quick look at the first few rows with df.head. You can see the structure here, a week, the ad spent in USD during that week, and the revenue in USD obtained from that week. Next, we'll use df.describe to get a quick statistical summary of the data, things like minimum, maximum, average, and standard deviation. This will give us a sense of the scale we are working with before moving on to analysis. We have 522 weeks of data in total. On average, weekly ad spend is around $7,750, with values ranging from as low as 500 up to a maximum of 15,000. For revenue, the average week brings in around $25,800, but the range is much wider, going from negative values in some weeks all the way up to 53,000. That negative minimum likely means that there were losses or reporting adjustments in those weeks, which is something to keep in mind when we build the model. Most ad spends fall between $4,000 and $11,000, and revenues typically land between $19,000 and $33,000. Now, if you notice something, the week isn't showing up here because df.describe summarizes only the numerical columns and week is the date field. And that is okay because for our purpose of training a model, we don't actually need the week information. What matters here are the inputs and outputs of the business problem. The input is how much was spent on ads, and the output is the revenue that came back. The week column is useful if we are analyzing trends over time, but for building a predictive model, it doesn't add value, so we can set it aside. To really understand the relationship between ad spend and revenue, let's plot them on a static plot. On x-axis, we have the weekly ad spend, and on the y-axis, we have the revenue that came back in that week. Each point here represents 1 week of data. What's interesting is that this does not look like a straight line relationship, right? Revenue goes up as the ad spend increases, but beyond a certain point, it starts to dip back down. This suggests that just throwing away more money into the ads does not guarantee higher revenue. In fact, after a certain level, the returns start to diminish. Let's start simple by trying a linear regression model. First, I'll separate the data. X will be our feature set, which has the weekly ad spend, and Y will be our target variable, which is the revenue. Then I split the data into training and test sets. About 80% goes into training and 20% goes into testing. Next, we fit a basic linear regression model on the training data. Now, even though we suspect the relationship isn't linear, this is a good first step. It gives us a baseline to compare against and shows us whether the straight line can capture the pattern we saw in the scatter plot. All right, let's actually plot our linear regression predictions on top of a scatter plot. Add a plot, which is a line passing in the training data along with the model's predictions. And I'll color it red so that it stands out. And here is the result. The red line is our fitted regression line, but look at how it cuts across the data. It's almost flat compared to the curve we expected. That tells us a straight line just isn't flexible enough to explain this relationship. Before moving on, let's quickly remind ourselves what the linear regression model is doing under the hood. The formula looks like y equals wx plus b. Here y is the prediction, which in our case is the revenue. X is the input feature, the ad spend, and W is the weight or the coefficient that tells us how strongly ad spend influences the revenue. Finally, B is the bias term, which shifts the line up or down. So when we trained the model earlier, what it was really doing was learning the best values of W and B to minimize the difference between the predicted revenue and the actual revenue. Let's check the parameters that our linear regression model has learned. First, the coefficient. It comes out to about minus 0.64. That means for every additional dollar spent on ads, the model actually predicts the revenue will go down slightly. Then the intercept is around 30,983. This is basically the starting point, which is the model's predicted revenue when the ad spend is 0. All right, let's try making a prediction with our linear model. I'll pass in a sample ad spend of 8,000 using model.predict, and the predicted revenue is about $25,800. Now, to properly evaluate the model, I'll import mean squared error from scikit-learn. I'll calculate the RMSE for both training set and the test set. Since mean squared error gives us the MSE by default, I'll raise it to the power of 0.5 to get the square root. So the model is consistent between training and testing, but the error is pretty high. On an average, our predictions are off by more than $10,000, which tells us this straight line isn't really doing a good job. Let's start with the data points again, each one representing a week of ad spend and revenue that came back. The data doesn't really follow a straight line. Instead, it rises, peaks, and then falls. That looks more like a bell-shaped curve, which in math terms is a quadratic curve. The equation of a quadratic curve can be written as y equals ax squared plus bx plus c. Here, we have introduced an x squared term, which allows the curve to bend. Now let's connect this with the general form of a machine learning model with two features, y equals w1x1 plus w2x2 plus b. The first feature, x1, is the ad spend, which is x from the quadratic equation, and the second feature, x2, will be x squared, which is the ad spend squared. And they have their own coefficients and a bias. So what we are really trying to do here is to introduce a second feature into our model, which is just a higher order term of the first feature. By adding this higher order polynomial feature, we are still using a linear model in terms of the features, but now the model has the ability to capture a curved relationship between ad spend and the revenue. This technique of adding the higher order terms is called polynomial regression. Now that we have introduced the idea of a second feature, which is ad spend squared, let's actually build it in code. I'll start by creating a new data frame. First column is the original ad spend, and the second column is the ad spend squared. You can see the result here. For each week, we now have two features. One is the original ad spend, and the other is a squared term. Next, I'll split this polynomial dataset into training and test sets, just like we did before. Notice that each row has two values instead of one because we've expanded to two features. Finally, I'll fit a new linear regression model on this expanded dataset. And that's it. Our model is now trained with both ad spend and the ad spend squared. This is polynomial regression in action. All right, let's visualize how our polynomial regression fits the data. On top of the existing plot, I'll plot the model's predictions in red. So we'll be able to see the fitted curve directly against the raw data points. And here it is. The blue points are the actual data, and the red curve is the polynomial regression fit. You can clearly see how the curve bends with the data, unlike the flat line we had earlier. Let's evaluate our polynomial regression model the same way we did before using RMSE. I'll calculate the RMSE on training set by comparing the actual revenue values against the model's predictions, and also do the same for test set. So here are the results. Train RMSE is about 7,916 and the test RMSE is about 7,029. Both are significantly lower than the errors we saw with the linear regression model, which were about 10,000. This confirms what we saw visually. The polynomial regression model fits the data much better and makes more accurate predictions. Let's take a look at the parameters our polynomial regression model has learned. The coefficients come out as 6.51 for the ad spend and minus 0.00042 for the ad spend squared. And the intercept is about 8,123. Now that we know the underlying weights, let's write our own predict function, creating a function named predict revenue that takes in the ad spend as input. I'll return the bias term plus the ad spend times its weight and the ad spend squared times its weight. We'll first do model.predict on 4,000. The predicted revenue is about 27,414. Then we'll call our custom function with the ad spend as 4,000, and we get the same result. That shows our helper function is working correctly since it matches the model's prediction. And this step is very important. By writing our own predict function, we see how the model is making predictions instead of treating model.predict like a black box. That also means if we are explaining this to our marketing manager, we are not only just saying that the model gave so and so number, we can walk them through the actual formula, how the ad spend and the squared term combine to produce the revenue estimate. This way, the manager understands not just the results but the reasoning behind it. That builds trust in the model's predictions. So we've trained our polynomial regression model, and it now captures the real curve between ad spend and revenue. But Notebook isn't the best way for our marketing team to use this. What they need is something simple, a page where they can enter a budget and instantly see the predicted revenue. So let's build a web app to make this model easy for them to use. We'll do this using Streamlit. First, I'll import Streamlit and give the app a title. Next, I'll add a number input box so the user can type in their weekly ad spend. I'll set a minimum value of 0 and a step size of 500. Then I'll add a button labeled predict. When this button is clicked, we'll take the entered ad spend and use our model to generate a revenue prediction. At this point, we'll plug in our custom predict revenue function into this app. So when the user enters an ad spend amount and clicks on the predict button, we'll call our function with that input, calculate the estimated revenue, and then display it nicely on the page. All right, now that the code is ready, let's launch the app. I'll run the command streamlit run app.py. And here's our web page. We've got the title, an input box to enter ad spend, and a predict button. Let's try it out. If I enter, say, $2,000 and click on predict, the model estimates the revenue at about 19,456. And the best part is the tool is now interactive. Our marketing manager can experiment with different ad spend values. For example, if I bump it to 8,000, the revenue jumps higher. If I push it further to 10,000, you'll notice that the revenue actually starts to decline, which matches the diminishing returns we saw in the curve earlier. So the app gives an immediate hands-on way to explore the model's predictions. So that wraps up project 5 of the series. We started with raw marketing data, built a linear regression baseline, improved it with polynomial regression, and then finally turned our model into an interactive web app that the marketing team can actually use. All the code and dataset are available in the repository link below. So feel free to try this yourself and experiment with different values. That was AI Lab 99. In the next project, we'll take on a brand new problem and continue building our AI toolkit step by step. Until then, happy coding.